Yes, we can start with the discussion forum. I have the doc file with me.
Okay, sir.
Yeah, I started the YouTube live, and in the YouTube chat, Nilima, you can check the YouTube chat also. One guy posted a doubt on it.
Okay, sir. Okay, sir. I will do it.
Sir, is it Nilima? What is the name? Like, is it Balaji sir, or who is that interacting with us?
Yeah, it's Balaji.
Yeah. So, like actually today we will be doing this technology testing, and we'll see how the format can be. Okay. Yeah.
Okay, sure.
Yeah, and then maybe we'll decide what should be the frequency of this live interaction and how much time, all those things that will be decided today. Okay.
Okay, sir. Sure, sir.
Yeah. So, Nilima, shall we start?
Yes, sir.
Yeah. So, 1 second. I have the doc file with me. So, what you have sent.
Yes, sir.
So, are there any questions now on the YouTube chat?
Yes, sir. They've started, but they're starting from clarifying the answers for question 6, 7, 8 of assignment 1. So, shall we start with clarification of questions from assignment, or shall we start from technical questions, which we get in discussion forum?
No, I don't have assignment in front of me, so you have to do maybe.
Okay, sir. So it's better, I think, we start from the concept questions which we got in discussion forum.
Okay, fine.
And then if something is required, we can do it in assignment, sir.
Yeah, so I'll go through that then. So in discussion forum, what I see is the first one is, can you give some examples of primary effects or like secondary effects? So that I think 2-3 questions are there like that. So secondary effects are mainly mainly due to the lateral deflection and self weight. That is P delta is a secondary effect. Okay, and then buckling is also another important secondary effect which we don't deal in this course structural dynamics. Okay, so first order stresses are directly like due to the loads applied on the members, like say axial force, bending moment, shear force, and torsional. So these are primary effects. And yeah, the second question is, how do we do nonlinear analysis by changing stiffness? So that has come. So here I would like to explain that. Say our equilibrium equation is, say, force is equal to stiffness multiplied by displacement. So that is what we usually use. That is static one. Now in dynamic case, our equation of motion is mu double dot plus cu dot plus ku is equal to force. That force can be any force, any dynamic force. In our case, say we have taken example as an earthquake force, that is minus mug double dot. So this is the equilibrium equation. So when we look at the equilibrium equation, just can I share my screen of that presentation so that it will be easy for people to understand it? Nilima, is that okay?
Sure, sir, you can share.
Yeah, so just 1 second, let me open that presentation. Yeah, I'll keep some presentations open and then I'll start discussion on that. Solution. Yeah, so 1 second, I'm sharing my screen. Yeah, can you see my screen, Nilima?
Yes, sir. Yes, sir.
Yeah, so I'll put full screen. Yeah, if you look at this slide at the bottom, so this is mu double dot plus cu dot plus ku is equal to P of T. So this P is the earthquake force or any dynamic force which is applied on the structure. Now, this linear or non-linear analysis is decided actually by this stiffness K into U, K into U. So static analysis is only Ku is equal to F. Dynamic analysis is Mu double dot plus Cu dot plus Ku is equal to P or F, whatever. So now, in nonlinear analysis, what happens is this Ku is equal to F. So this Ku is, that is a force which is the function of displacement as well as the history of displacement. So that is velocity also comes into picture in case of this one. Now when it comes to nonlinear analysis per se, not a dynamic nonlinear analysis, static nonlinear analysis. So that static nonlinear analysis is again Ku is equal to P. Ku is equal to P. Now, usually what happens is, if you can like follow what I'm going to say right now, if we have to find out displacement, that is the effect of load on the structure. So U is equal to K inverse P. U is equal to K inverse P. So that is, just one second, let me open another. Yeah, this one. Yeah, so this is linear analysis. So in linear analysis, so loads are well within elastic range of deformation and superposition principle is applied. So as you can see, I can apply say some, one second. I can apply say some load, say P is equal to 5 kilonewton and find out the deflection. And later I add say another 5 kilonewton and find out the deflection. And the third case I can put total 10 kilonewton load and check the deflection. If I add two deflections, that is due to 5 kilonewton and 5 kilonewton, and check with the 10 kilonewton deflection, addition is equal to the total deflection. So that is clear. But in nonlinear analysis, that doesn't happen. Why it doesn't happen? So the reason is, in nonlinear analysis, if you can check here, say P is equal to the first, this arrow you can see, pointer.
Yes, sir, it's visible.
Yeah. So if this is say 5 kilonewton, and then this is say another 5 kilonewton, that means total 10 kilonewton. Here you can see this line, okay, is not going in the like with the same slope. So after yielding, this slope is reducing. So slope is reducing compared to this like tangent. Tangent is reducing. It's not 90 degrees. It's not along this one. It is slowly reducing, and as it, when it comes to the peak, it will become horizontal. So what is happening is stiffness of the system is coming down. Now, how the stiffness of the system comes down? So stiffness of the system is mainly dependent on moment of inertia of the cross section, length of the member, as well as modulus of elasticity. So these are the three things, and boundary conditions. So these are the four items which decide the stiffness of the system. So now that reduces. So in nonlinear analysis, what we do is first we find the like deformation, and from deformation we find using strain displacement relationship. That means strain displacement relationship will give us a strain, and after that we use a compatibility equation, that is stress strain relationship. And stress strain relationship is like like if our assumption is only up to linear, then we will calculate up to that. But all materials are non-linear when we test them. So then stress at that point, stress and strain are not linear. So that stress we have to calculate, and then that stress multiply by area will give us the reaction. This reaction is not equal to the applied load. So usually applied load is more, reaction is less. So that is the error in calculation. The reason why that error is coming because of the non-linearity. So that's why in nonlinear analysis we need to do step by step, that is many iterations, so that we will hit the right point on the curve. So that is like quite involved process. So in this basic structural dynamics code, that will not come. So that is one thing. Yeah. 1 second. How to remove the sharing of the screen? Yeah, stop sharing. Okay. Okay, that is the second question I've seen. Then some typo errors are there. I have already clarified Nilima. Fourth question, that is K1213 and K23.
Yes, sir.
And then the next question is on static condensation. Okay, let me open that slide and show it to you. Static condensation. 1 second. Degrees of freedom. Sharing my screen once again. Okay, can you see my screen? Ilma, can you see my screen?
Yes, sir. Yes, sir. It's
yeah. So static condensation is actually removing the unwanted degrees of freedom. That is called static condensation. That means we are removing the degrees of freedom which are unwanted. Now, what is the definition of unwanted degrees of freedom? Unwanted means the degrees of freedom to which mass is not assigned. That means inertia force is not generated at that location. So that is unwanted degree of freedom. Now, if we look at this structure, forget about all the other dimensions, EIC and EIB, just if we remove those things, okay. So anyway, next time I will try to show the board also and try to write that. So today anyway, we are trying to test the technology and the format. So anyway, let's come to this part. Is a single bay, single story portal frame. So what happens is, in this one, every degree of freedom or every joint which has, 1 second, if I have that, I'll show. Yeah, so this is static indeterminacy. Let me, kinematic indeterminacy. If you look at kinematic indeterminacy, sum of the degrees of freedom of the nodes and then subtract those degrees of freedom that are constrained. Okay, so let's take this definition. What is the definition of degree of freedom? Let's look at that. It is saying that two-dimensional structures will have 3 degrees of freedom at each node. Three-dimensional structures will have 6 degrees of freedom at each node. So when we say take two-dimensional structure, like how it will move in plane. So x direction, y direction, and rotation. So 3 degrees of freedom at each node. So in that manner, if we come to this, Ilma, are you able to see this portal frame?
Yes, sir. Yes, sir.
Single story. Now here, yes, there are total 4 nodes. Say node 1, node 2, node 3, node 4, or joints, you can say joint 1, joint 2, joint 3, joint 4. So actually speaking, every joint will have 3 degrees of freedom. okay, in this 2D plane frame. So total 4, 1 second, let me take the laser point. So here 3 degrees of freedom, here 3 degrees of freedom, here 3 and here 3. So total 12, 4 joints into 3 is equal to 12 degrees of freedom. And what we need to do is remove the constrained degrees of freedom. So constrained degrees of freedom means here A, B. So total 3 plus 3, 6. Out of 12, we need to remove this 6. So we are left with 6 degrees of freedom. So where these 6 degrees of freedom are there? 3 at point C, joint C, and 3 at joint E. No, sorry, D, joint D, C, D. Now here, one is X direction. Here, one is vertical direction. Then third one is rotation. So if I push this, say, degree of freedom, so what will happen is the entire beam will move, okay, as a free body, as a rigid body. Then there is a rotation here, and then there is elongation of column. So usually in ordinary structural analysis, we don't consider this extension of column. That means column deformation. So degree of freedom of column here and here we will ignore or remove. So that we are left with how many degrees of freedom? Out of 6, we remove another 2, so 4 degrees of freedom. And then if we say this horizontal direction degree of freedom movement and here horizontal movement, both are same because rigid body motion is taking place in beam. So this one and this one, so that means horizontal movement of like at node C and horizontal movement at node D, they are one and the same. So we can merge them and make 1 degree of freedom. So that's how rotation at node C, rotation at node D, and translation of this one. So all put together, that is 3 degrees of freedom. So that's how we get this 3 degrees of 6 degrees of freedom will become 3 degrees of freedom. So that 3 degrees of freedom, if you can see the matrix here, 3 degrees of freedom. Okay, that 3 degrees of freedom are U1, U2 and U3. Now, if we are not lumping the mass at these nodes, lumping the mass in the center, then we don't need U2 and U3 because there will be no inertia force generated at that location. So only translational direction. So that is the reason why we convert that into single like degree of freedom system. So now removing unwanted degrees of freedom. So what degrees of freedom we have to remove? U2 and U3 we have to remove. So here U1 is corresponding to this first row and first column. So this one will be removed. So that is that 6h square, this portion you can see. Force will be generated here. So this static condensation by using this method. So we will have only the equation which is containing U1. Okay. So that is static condensation. 1 second. Yeah. Then the next one is 10 second law. Yeah, another simple question. Do all computer softwares use stiffness matrix method for analysis? Yes, usually most of the softwares use a finite element approach for solving the equations. Okay, finite element approach. And yeah, what is type of earthquake vibration? Is it free vibration or forced vibration? So definitely it is forced vibration, and also undamped or damped vibration. That is a question. So undamped vibration will not take place in real systems. Real systems will always be damped vibrations. Okay, but we will consider for learning sake, we'll say undamped free vibration. But all the structures are damped vibrations only. Degrees of freedom. I think, Nilima, I think these are the main questions in this the document what you have sent, discussion forum questions. Now, if there are any questions on the YouTube chat, you can now take.
One question is about nonlinear, I mean, restoring force in nonlinear case. But that is, I mean, you have answered that question when you are explaining that stiffness equation.
Okay.
If you want to clarify further, we can take up. Or second question is for the frame which you have explained the stiffness matrix. Question is about how many degrees of freedom for a hinged frame if frame is having hinge supports.
Frame is having hinge support. Now it is the number of degrees of freedom depends on, say, our idealization. So for example, if we take a building, okay, building, say one frame in the building, and that frame building is of say single bay 3-story. If you take single bay 3-story, how many nodes will be there? At the base, two nodes. At the base, 2 nodes are 2 joints, you can say. And then first floor level 2 joints, second floor level 2 joints, third floor level 2 joints. So total 8 joints are there actually. So total number of degrees of freedom we can count as 8 into 3. So 8 into 3 is 24 degrees of freedom. Now this 24 degrees of freedom, now at the base, these 6 degrees of freedom are already restrained. So we remove that. So 24 minus 6. So that is 18 degrees of freedom. That means first floor to, second floor to, third floor to. Now out of this, if we are lumping the mass at the center of the slab, if we are lumping the mass, then we don't need axial extension or shortening of the columns. So thereby, like this one. So x direction, y direction, and rotation. X direction, y direction, and rotation. So we can easily remove this y direction without because we are not considering the axial extension or shortening of the column. So how many we can remove? 1 here, and second here, third, fourth, fifth, sixth. So total 6 we can remove. So out of 18, we can remove another 6. That will become 12. And then because mass is not assigned, so rotational degrees of freedom also we can remove. So that will be, we will be removing another 6. So it will be, we are left with only 6 degrees of freedom. Now translational x direction at one node, translational at another node, both are same actually, because beam is moving in a rigid body motion. Both are same. So that's why 3-story structure will have 3 degrees of freedom system. So the 3-story structure is 3 degrees of freedom. So that's how we decide. And how to calculate the stiffness of that? So I've already explained that column, and when we move it laterally, the stiffness of the column will be 12 EI by h cube. So in n number of columns, you can directly add all of them and sum of all the columns in that direction. Sum of the individual stiffness of all the columns in that direction. So that's how it will become 24 EI by h cube. 12 EI by h cube into number of columns. Like assuming that all the columns have same cross section area and same length, same height. So that is how you get the degrees of freedom and floor stiffnesses. Am I clear?
Yes, sir. Another question is that like there are many methods to remove unwanted degrees of freedom. How to choose which method to use?
The method such as suggested in the video is quite appropriate. I think you the question may be related to matrix operation. So matrix operation, you can use any method. So that's not, and there are so many subroutines available right now. And while doing hand calculation, the method suggested is very useful. So like 3 simultaneous equations you can take and do it. Okay. Or say any elimination method also you can use. That is just up to our choice. And in computer programs, it already does that optimization. So yeah, that's the answer.
Okay, sir. There is a general question that is structural analysis a prerequisite for this course?
Yes, if structural analysis is studied, then structural dynamics will become easy. Otherwise, as and when we discuss any topic, at that time also you can brush up.
Okay. As of now, there are no further questions in the chat box. The YouTube video is running little with a small lag. So maybe if we wait for a few minutes, maybe questions will pile up.
Okay. Yeah, I think some 10 seconds lag is there. Hello, Nilima, can you see how many are viewing right now? That shows.
Like in Zoom meeting, there are 7, including us, and in YouTube, no, I think the same number is there, 7 number only.
Okay.
So whoever is attending in Zoom are all also present in YouTube. That's it.
Okay, then.
And
can you unmute if they want to ask directly? Just unmute them. It's because the number is less.
okay, sir.
Hello.
Hello, good afternoon, sir.
Good afternoon, sir.
Yeah, good afternoon. So, how is the course going? Are you able to follow the course properly?
Yes, sir. Yes, sir. It's
Okay, good. And feel free to ask questions. Okay, any question is okay. So, if question pertains to structural diagrams, TS will answer, and I will also try to. And
sir.
today we are trying actually testing the technology, and what we are going to do is when is the appropriate time and what kind of questions and what should be the format. Actually, I'm very much used to writing on the board. Whenever you ask a question, I wanted to draw or explain there. So maybe now I'll try that technology. We'll see. Echo is coming today, so that's why I could not write, but I'll show the presentations. So any specific questions you have on any of the weeks? I think the third week is running right now, right?
Fourth week, sir. Fourth week is also there.
Fourth week is also there. Okay. So which topic you understood nicely, or which topic you feel you could not get much?
Sir, that half power bandwidth was a bit tricky. Otherwise, everything is known.
Acha, okay. Now let me tell you the answer to that. Actually, half power bandwidth is like we have, say, that amplitude curve. In amplitude curve, what it says is the delta omega. Delta omega means the delta omega means like where the energy is maximum. That bandwidth we need to capture. So that is like 0.707 of the peak, actually 0.707.
So how that was decided? Sir, how that was decided that it will be 0.707 only?
That is the frequency. So it has this has come from the vibration theory. So that is the frequency at which this much is the maximum value. So that's how we decide peak frequencies, means frequencies at which the structure's response gets amplified. So in that band, so more energy is contained in that band. More structures will be affected more in that band of frequencies.
So we not only have to make sure that our structure is not in a resonating mode. In addition to this, we have to also see this also, that the structure is not in this band.
Exactly. Now let me give you one simple example. Say if we take say earthquake, so you can understand earthquake signal. You can understand.
Yes. Yes, sir.
So there is earthquake time history. What we can do is to understand this half-hour bandwidth. You convert that into Fourier transform. So time domain Fourier transform means you are converting the axis, time axis to frequency axis. So what it says is at every frequency, what is the energy contained in that earthquake vibration or earthquake signal. So we have that. So it goes like up and down kind of thing, or sometimes it will go wide. Sometimes there is a peak like this. So these are the Fourier transform. So whatever we may get from the earthquake signal. Now we have to ensure that our structure is not falling in the peak of that. Then actually there are three things. One is amplitude, another one is frequency band, and how much time our structure is present in that frequency. How much time? So these three things decide. But in this half-hour bandwidth, we are deciding only like peak amplitude and the frequency band. There is no time in that. How much time the structure is present in that component is not there in this one. Okay. So
no, but then I mean, like, sir, like our time history has say 0 at 0 time I have some acceleration, at 0.0 time I have some acceleration. So you mean to say that this, say if that earthquake is for 30 seconds, this 30 second will be converted into frequency from 0 to 30.
No, not that. No, not that. Let me explain you. See, this 30 seconds is the signal time, right? Signal
yes,
time
sir.
30 seconds. Now, when I convert, my Fourier transform will have frequencies. Say 2 hertz frequency, 3 hertz frequency, 10 hertz frequency, 20 hertz frequency, 100 hertz frequency. We cannot say that it will be minus infinity to plus infinity. Sorry, 0 to plus infinity. That is the range. So when I do the transform, then only I know what is my range of frequencies. The time series time has nothing to do with this frequency range. So
that I can select. The frequency range I can select.
Yeah, you got no.
Yeah.
You will not select it. You will get from the signal only.
Okay.
So suppose say you have one ground motion which has frequencies from say 0 to 20 hertz only. Another ground motion, you have frequencies from say 0 to 200. Another ground motion will have frequencies from 0 to, ground motion is some vibration. All ground motions will not have that. Some vibration which have frequency, maybe very high frequency. But when it comes to buildings, now you can understand that. So our the number of floors will be from where to where, you imagine and tell. Number of floors of the buildings.
Say 3-floor building.
3 floor, 1 floor, no, 1 floor, no, starting from 1 floor.
Yeah,
starting from 1 floor to say, let us assume 50 floors, 60 floors, 100 floors, right? So
yeah.
Usually 1 floor building will have say 0.1 second. This is rough estimate I'm telling. 0.1 second is the frequency, natural period of the building. And on the other side, 100 floor building will have say around say 8 seconds or 10 seconds.
10 seconds.
So 0.1 into n is the rough estimate.
Yes.
But as the building height increases, its stiffness will be more, natural period will be slightly less. So it will become stiffer. So let us take from 0.1 second to 8 seconds. Is that clear?
Yes.
So total buildings have come now in 1 story, 2nd story, 2-story building, 3, 4, 5, 6, like that. 100-story buildings have come in that range. Now this natural period 0.1 second to say 8 seconds. If I inverse them, what will happen? 1 by 0.1, 1 by 8. or 1 by 10,
Yeah.
let us take 1 by 10. 1 by 10 is how much?
0.1.
The 0.1 hertz is, this is 1 by 0.1 is how much?
10.
Okay, so now this hertz, sorry, this is that hertz, that is like what do you call? T, 1 by T is frequency.
Frequency.
1 by T is frequency. Now that frequency, say smaller one is here, larger one is here now. So I reverse it.
Yes, reverse.
Okay, so now three-story structure will have what natural period?
0.3.
So now how many hertz it will be?
1 by 0.3. 30.
1 by 0.3 is 3.
Oh, 3. Sorry.
3
3.
hertz. So 3
3
hertz,
hertz.
4 hertz, 5 hertz, 6 hertz, 7 hertz, like that. This is the hertz. Okay.
Yeah.
This is the frequency F. If I want to get omega, so I need to multiply with 2
2 by
by F.
5.
Right? So now,
Yeah.
when I get the earthquake signal, I get this in what frequency, how much energy is there.
Okay.
That's one input. Now I have to ensure that where my building is falling. So at suppose say 10 hertz, 1 hertz, 5 hertz, 20 hertz, I have to see where it is falling. Now if my building is falling here, but peak of the frequency is here, I need not worry. If my building is falling here and peak of the frequency is lying very near to that,
Need to
I
worry.
need to worry. Now I need to worry because of two things. One is where it is lying near to that peak frequency. So how much near, that is 1 by root 2 of the peak. So if I draw a horizontal line, I'll get the band.
Yeah, got it.
So that one, and then also I have to see the maximum value also. So these are the two things I see. So whenever we do structural analysis or structure and design, we need to see in the vicinities. For important structures, I am telling, say more than 30 floors building, we need to do site-specific analysis and find out what kind of frequencies will be present in the ground motion. If at all earthquake occurs in that area, based on that, we should design the building.
Right.
Okay,
Got it. Yes.
It has link. Yeah.
Right.
One more thing, or one more important thing, let me explain. Say this, there is a damping is there, no? Damping.
Yes.
So damping and frequency, these two things are, there is a connection. Say one analogy or one example I'll give you. Say if you, on the beach, if you stand, you will leave your footprints, if you stand there.
Yes.
Okay. Now, if you run on the beach, footprints will not be there.
Okay.
So now, what is happening? The sand needs time to respond. So speed is so much that we are not allowing that not allowing
impression to go deep.
That is the thing. So now, if frequencies, damping, and amplitude, these three we have to look at together.
Okay.
So that is why, like, there are so many applications, motors, fans, or in this damped forced vibration. You can see these examples. So when we start a motor, it is picking up its RPM from 0 to 2000.
Yeah, that you explained in the numerical. Numerical, you had explained.
So that is the thing. So it needs actually it needs time to respond. So
but in our problem, then the beam will get damaged if our
exactly. So now if the machine is vibrating at the resonating frequency of the foundation, then it will get damaged.
Yeah, true.
But if it is just passing through that frequency, it won't get damaged.
Okay.
Yeah,
so you have to make sure that it passes through.
We have this problem.
Okay. So you have to make sure that it just passes, it doesn't stay over there for longer time.
Exactly.
Okay.
And also that final RPM should not be within the range of that half power bandwidth again.
Okay. No, but some other technique, like a retrofitting technique or some technique can be done that so that it doesn't come in the interface.
Much simpler thing is we should just keep it away from that frequency band. That's all. So by introducing damping, lot of amplitudes will come down. Peak amplitude will suddenly come down. So main thing is in machine foundation, we need to see whether we are giving a proper provision for damping or not. The moment we give proper provision for damping, amplitudes will come down. That is anyway safe.
Okay. Okay.
So any other question from?
And a few questions in assignment is also they are not matching the answer.
Acha. Okay. I think I'll check with Nilima. Okay, I got TS. Okay.
And and in question number 5 also, option is not matching, so we just gave a fluke for that because that option, exact option was not.
We will check that. Okay.
Okay, sir. Thank you. Sir.
We will check that. Yeah.
Thank you, sir. Thank you, sir.
Yeah. Any questions from Akhileshwar Shahi?
Hello, good afternoon, sir.
Good afternoon.
I'm new to this structural dynamics. Okay. So I made this week 1, just I went through the week 1 course.
Okay, fine.
And the assignment.
Break the rhythm, you attend every day.
Yeah, I attend every day, but I started late.
Okay.
So I just passed the week 1.
Yeah.
So there was an assignment. One question was where the base was hinged, and there was a 2-column portal frame. The mass was on the top beam. So I considered the stiffness of one column as 3 EI by H cube. And for 2, I added this 2, sum of the 3 plus 3, 6 EI by H cube. But my answer was not correct. Why was this? Okay,
we'll check, sir. So we'll look at that and check and then get back to you. Okay.
Okay.
Yeah.
And also there was one more question. When 2 springs are in one system, one was the cantilever, and one weight was from the spring. So how we calculate that stiffness? Because in the lecture was not given.
Cantilever is there and there is a spring, right?
Yes.
To a cantilever beam, there is a spring attached, right?
Yes.
And then there is a
weight.
Okay, so that system will be springs in series.
Yeah, spring in series. So one is K1, one is K2.
So then equivalent stiffness will be actually 1 by equivalent, K equivalent is equal to 1 by K of beam plus 1 by K of spring.
Oh, okay. Actually, this was not in the lecture, but come in the assignment, so I could not find the answer.
Acha. Okay.
Thank you.
Thank you, sir. Thank you. Yeah. And yeah, Mr. Venkatrao, you have any questions?
No, sir, I have no questions, but I have doubt in my research. I'm doing.
No, that I think we can discuss later.
Later, okay.
Yeah. No, any questions pertaining to structural dynamics you can ask.
No, it is very interesting, sir.
Okay, fine. Yeah, any questions till now? That is 3 weeks are over. No? Any questions in that is fine. And whenever we complete 4th week, we will include 4th week also, up to 4th week, next up to 5th week, like that we will continue. What do you suggest the frequency? Say once in 2 weeks is okay, or once in a week we should put, or after enough number of questions are there in the discussion forum, we should put this one live. So what is the suggestion?
I think once a week is okay.
Okay, right. So like if say I get enough number of questions in the discussion forum, then I can look at those questions and come up with the answers. So that will be a good thing. So let me see. And preferable time, what I suggest is morning session of Saturday. How it will be for you?
I think the second half is good, 2 to 5.
Achha, this one is better. Okay.
Yeah, this one is better.
2 to 5 is better, sir. Why? Because morning time we have college.
Achha, okay. So then we'll stick to this time only. Okay. I think Nilima, we can conclude here for today.
Okay, thank you very much, sir.
Yeah, thank you. Balaji sir?
Yes, sir. We will close the session.
Yeah, thank you. Thank you so much.
Thank you.
Thank you. Thank you very much. And all the people who are attending this course, thank you so much.
Thank you, sir.